Hello and welcome back to one final video for the Net 1010 module in Robotics 10. Today we're going to take a look at some more ICs, some different kinds of circuits we can make, and then I'm going to turn you loose to just kind of experiment and play around and then show me what you come up with. So let's flip over quickly to our workbook and see what we're up to next. So today we're talking about the 555 IC. And if you have any parents or relatives or friends who work in electronics or studied electronics in the past or do it as a hobby, and you mention to them that you're playing around with 555s, they'll know exactly what you're talking about, because this is probably one of the most ubiquitous ICs out there. Everyone knows about it. It's a very common first exercise in ICs, but also very useful in all sorts of applications. And we'll see one of those applications today. What we're going to do today is make this circuit with the 555, which is another oscillator. We saw in a previous video how you can make an oscillator out of just NAND gates. That circuit had the limitation of having a fixed duty cycle, it's called, which is simply the percentage of time that the output is on versus off. So whatever frequency that oscillator is oscillating at, going up and down, back and forth, it's always on for the same amount of time as it's off within each of those pulses. There are applications where you might want to change that, either by having a signal whose duty cycle actually changes as the signal goes on to send some kind of information. And that's something called pulse width modulation, which we'll get into in Robotics 20. Or just some applications need a specific duty cycle on the signal to be used as a clock for some other logic going on elsewhere in the circuit. And the 555 oscillator that we can create here allows us to have that kind of control over the duty cycle of that output. It's a bit smaller of a package as well. You'll see here from this diagram, it's only 8 pins as opposed to the 14 pins of our quad NAND gate IC. About the same amount of hardware though. We've got 2 resistors, 1 capacitor, and 1 kind of extra bonus capacitor that's optional, and about the same number of connections using just jumpers as well. But I'll also briefly talk about at the end how the 555 can be used in some other interesting ways if you hook it up a little bit differently. But first, let's talk about how we'll actually make this circuit here on the breadboard. And you'll notice I've given you 2 diagrams. The one on the left is the actual circuit diagram, the schematic, which tells us, once again, the connections between all of the pins and any additional hardware we're going to use, like these resistors and capacitors, as well as connections to voltage and ground. But this diagram itself isn't spatial. It's laid out in a visual way so that it's easy to see all of these connections, but the locations of these pins on the chip do not match up with where they actually are physically on the IC that you have in your hands or in your kit. So that's where this other diagram comes into play, and we've seen these before. This is called a pin out, which just gives us the labels of what each pin is. And so using this diagram and this diagram together, we can construct this circuit. If we want to know, okay, we need to connect this discharge pin through a resistor to 5 volts, we'll have to find where the discharge pin is here. We'll notice it's pin 7, and that's the one that will actually connect up to 5 volts. Notice on this diagram, discharge is on the right, and over here, discharge is on the left. So don't trust the positions of this left diagram. This is just to tell you about the connections, and this tells you about the positions of those actual pins. So let's see this in action. I'll show you how we hook this up on a breadboard. Of course, you can do it in a more compact way or a more spread out way that makes it more visual. It's up to you, but I'll show you one way to connect this all up on the breadboard, talk about some considerations and see what this does, and then see how we can change this to modify that output. So we'll flip over into Tinkercad circuits here. You can do this on your breadboard. And I've already got the Arduino set up, connected 5 volts and ground to the breadboard, and got my 555 here. Once again, we notice that this IC has a little notch in the top, or maybe it has a little circle here. Either way, something to tell us where we start counting. And so this would be pin 1, 2, 3, 4, and 5, 6, 7, 8. And the nice thing in Tinkercad circuits is I get each of these pins labeled. You don't have that in real life though. That's why, of course, we have the pinout diagram. So let's start just working our way around this schematic and making each connection that we see. I find this to be the easiest way, is just kind of pick a point on the diagram and start working around in either a clockwise or counterclockwise direction until we make every connection that we see. So the first thing, very easy to see here, is the VCC pin and the reset pin are connected together, and they're also connected to 5 volts. So there's a couple ways we could do this on the breadboard. I'll go over a few of them. First, let's make sure we know what pins we're dealing with. VCC, which is just the kind of code word we use for power or positive voltage, is pin 8 on our pin out, and reset is pin 4. So we're going to connect pin 4 and pin 8 to 5 volts. By that circuit diagram, the schematic diagram, we could connect pin 4 to pin 8 and then pin 8 up to positive. This works. You could do the exact same thing, accomplish the same thing electrically by connecting pin 4 to 5 volts and pin 8 to 5 volts. Both work. Either way, it doesn't matter. I'm going to do this just because it's a little cleaner. So just a little jumper that's going to hop over my IC to connect 4 and 8 together. And I will color code these red to indicate that they're going up to 5 volts. So we've done this little segment here. Let's keep moving around. The next thing that I see is we've got a resistor. And where is it connecting to? It's going from discharge and around. And I have some options here. I could either connect it to reset, or I could connect it to VCC, or I could just connect it to 5 volts. And that's probably going to be the easiest way. Let's make sure we know where discharge is. Once again, that's pin 7. We already saw that. So we're wanting a resistor from pin 7 up to 5 volts. And what kind of resistor? Well, I've labeled it here as a 10K ohm resistor. So let's go find that in Tinkercad. We'll grab a resistor from pin 7, that's this one, up to 5 volts. I'll just make this 10K. Once again, yours are different because yours use the 4-band color code system and these are the 3-band color code system. So your 10K ohm resistors are the one with the single red stripe in the second position in. And that's going from pin 7 to 5 volts, and that makes this connection here. We can also see from discharge another resistor that goes down to here. And where's that going to connect to? Well, it looks like threshold and trigger are both connected together, and this resistor can connect to either one of those. The diagram shows into threshold, but it could just as easily go into trigger, and that would be the same because we'll see that trigger and threshold are connected together. You could also just connect all 3 of these out to some additional row in the breadboard if that makes it easier for you. I'll make this a little bit compact though, and just go from discharge into either threshold or trigger. So let's make sure we know where those are. And maybe the easiest thing to do first will be just to connect trigger and threshold together. So on my pin out, trigger is pin 2 and threshold is pin 6. So here's pin 2 right here, and here's pin 6 threshold. So I'll just connect those up. I'll use green because this is just an internal signal, so it's not red for 5 volts and it's not blue for ground. And now I can go and get this resistor that I need. And we'll take another look here. We've got to go from discharge, which is 7, to one of these 2 that I just connected together. And so if I was to go from 7 to 6, that would be a little tight to fit a resistor in there. So I think I'll go from 7 to 2 to make that connection. I'll make these gray so it looks like the legs of the resistor. So I've just got this resistor kind of hopping over the IC, just like my jumpers, and just being careful it's going from 2 to 7, while I have this jumper going from 2 to 6. It's coming together here. We've got this top left corner of the circuitry already all done, so just this section left to do. So we see another connection here from the threshold trigger junction, and that's this capacitor C1. And we'll see from the label C1 is a 10 microfarad capacitor. The 10 microfarad capacitors that you have are the polar capacitors. That's this one, the big cylinder, and it's got a stripe on it. Once again, make sure you look very closely. You're looking for some letters on this that says 10 UF. It says a bunch of other stuff. It is like an IR receiver or something. And so don't use that. Make sure you've got the capacitor. And in this diagram, it doesn't indicate the negative, but we do see that one of these sides of this capacitor is going to go to ground. So I'm going to make sure I hook up my negative leg of this capacitor to ground. The positive leg of the capacitor can go to threshold or trigger. Let's see what makes sense here. If I'm going to have this kind of here, I'll bring the negative to ground, and probably makes the most sense just to connect the positive here to pin 2, which is the trigger pin. So there's that capacitor. Make sure you have this the right way around. If it's not working, when you plug it all in, double check that this is the right way around. So there's that. Next down here, we have ground, connects to ground, obviously. So where's that? Pin 1. So pin 1 is here. I'll just move my capacitor out of the way a little bit so that I can get pin 1 to ground nicely. Color code that blue. So with that 5 volts here on pin 8 and ground on pin 1, this IC is powered. So you definitely want to make sure you're doing this with the Arduino unplugged, because as we're making some connections, there's a possibility to short some things in some weird ways, potentially damage the IC, especially once you have it powered with both 5 volts on pin 8 and ground on pin 1. But we're not quite done yet. We'll see still over here, we have an additional connection from this control voltage pin, which is pin 5. And that's through this small capacitor, 0.1 UF. That's the small little ceramic one. And it's just going to ground. This one's actually optional. It's just to kind of stabilize everything and make sure there's nothing flickering in terms of the overall power to this IC. In this application where we're just flashing an LED, not terribly critical. If we wanted to have a clock that was very stable, so we don't want the duty cycle changing at all or the frequency changing at all, this could be important. Just having this capacitor here just smooths out the overall voltage input to the IC. You can put it in, you can leave it out, it's up to you. If you were to put it in, it would be one of these little capacitors. Yours is brown. We're using a 0.1 microfarad capacitor. I think yours are 0.1, they might be 0.01. Either way, it doesn't really matter. And this schematic is telling us to connect it between control voltage, which is pin 5, and ground. So here's pin 5, here's ground. So we've done all of the circuitry to actually get this thing operational. There is now an oscillating signal on our output pin. And if we look at the pin out, the output pin is pin 3. That's the only pin we haven't used yet. And you can see from this diagram, I've indicated to connect a resistor and an LED to pin 3 so you can visualize that signal. So let's go ahead and do that. I'm just going to bring a jumper way out here just to make things a little bit more clear. Get this out of the way. So what we'll need is a resistor. Remember, for LEDs, we typically use 220 ohm resistor in your kit. Yours will be the one with 2 red bands, just like mine, but there's 2 additional bands afterwards. And then the LED to ground. Of course, make sure your LED is the right way around. Remember, the long leg is the positive one, so that can connect up to the resistor, short leg to ground. If you have snipped the legs of your resistor for whatever reason and you don't know which one is the long one, you can also remember that the little plastic casing around the light itself, this rim that it has gets flat on one side, and that flat side is the negative side. And you can see that actually even in this diagram here in Tinkercad. So if we hooked everything up correctly, we should be able to give power to the Arduino and see a flashing light. Let's see if Tinkercad can actually handle that calculation. And it looks like it is flashing. Not terribly stable in here. It's probably going a little bit too quick for this simulator to deal with. Yours will be flashing probably around 5 times a second. So you should be able to see it with your eyes. If you can't see that flickering, if it's going too fast, let's talk about some ways that we can play around with this circuit and make that flashing a little bit slower. Whenever you want to learn more about a piece of hardware and electronics, the best place to look is the datasheet. So for our exercises, I've just given you the pinout diagrams and schematic diagrams, but where all this information comes from in the first place are files known as datasheets. And I've put the datasheets for all of the ICs that we're using in this class into the D2L. If we look at the datasheet for the 555, we will notice it is 37 pages long. Okay, a lot of information, weird looking graphs and charts, and way more information that we would ever need for what we're doing. These data sheets cover absolutely every little piece of technical information about the IC, but is usually overkill for most people. Some important things you can find in a data sheet though is of course the pinout. And of course, this is where I got the pinout for your workbooks. I just took a screenshot of this and copy pasted it in. You can also find all sorts of information about operating voltages, things like that. You can sometimes find sample applications of how to hook it up to do certain things. For example, here's a schematic diagram that looks fairly similar to what we're using to create a clock signal. There's some other examples in here of other things that you can do with the 555 and how they work. But one thing that we can find in here, which is really handy, is for this particular circuit, they've actually included a calculation of how you would be able to figure out the frequency based on the resistors and capacitors that you use in this setup. And we can see they have the same setup where they've got the resistor here from positive to discharge, and another resistor here from discharge to threshold and trigger, and then a capacitor down to ground. And so we could probably assume that this calculation is pretty close to what's actually going to happen with ours. We're not going to go through the math here, but one thing we'll notice is we'll see that the frequency is roughly equal to some constant, 1.44, divided by this math, which is the sum of these resistances times the capacitor. So what we know about this then is if we increase the capacitor, make a bigger capacitor, then that's going to make this number bigger, but then we're dividing it, makes our frequency smaller. Low frequency is actually long amounts of time. A frequency is just a number of times per second. So if we have right now 5 times per second, our frequency is 5 hertz. If we were to increase the capacitor, that might go lower, maybe to 2 hertz or 3 hertz. So it would be going 2 or 3 times a second. So we'd be able to see it more clearly. Same thing as if we increase these resistors to bigger resistors, we're going to get a bigger number here, but then it's on the bottom of a fraction, so it's going to result in a smaller number for the frequency. So we'll get a lower frequency, which means, once again, a longer amount of time in between each pulse. So let's see that really quickly in Tinkercad. Easiest thing for me to do is just change this resistor for a bigger resistor. Now I'm just going to do this to a 1000 kilo ohm resistor and see what that does. And now we can see nice long pulses. I believe you just have 220, 1000, and 10,000. So how could you change this around? Well, the easiest way to make a bigger resistor out of smaller resistors is just to put them in series. So if I take this resistor and instead of connecting it straight across from here to here, I'll just connect it up to another row and then grab another resistor. I'll make it also 10,000 ohms and we'll connect it from the first resistor to where it was initially going. So now I've just got a 10,000 ohm resistor and then another 10,000 ohm resistor in between these two, which is electrically the exact same thing as a 20,000 ohm resistor. When you have resistors in series like this, you can just add their resistances together, and that's the total resistance. So we've gone from 10,000 to 20,000, and we should see a slower flickering. And you could add more and more of these in series to make more and more resistance here to get a slower and slower flashing LED. Another thing you could do to play around with the resistance is instead of using just static resistors, you could use a variable resistor, like a potentiometer. So if I hook up a potentiometer here, let's still use this initial 10,000 ohm resistor so we just get more resistance. The ones that you have in your kit are also 10,000 ohm potentiometers. I'll hook up my resistor to the middle pin of the potentiometer, and then one of the outside pins, I'll just jump over to where this resistor was initially going. And now if I start the simulation, we should be able to see that if I turn the knob, I get a faster flashing LED, and I turn it back the other way and my flashing slows down. So you could control how quickly that flashing is occurring using a potentiometer like this. So those are just a few ways that you can kind of play around with the 555. I'll just set this back to the way I originally had it here. And we can actually get rid of this just to make things more clear. The absolute bare minimum that you need to get a flashing light on a 555 is this circuit. So just our 2 resistors and our capacitor. We've got 3, 4 jumpers, and then whatever else you need for your output. So very simple, very straightforward. The 555 is a great little tool to have whenever you need a clock signal. If you need something that's oscillating, you can use the 555. There's lots of audio like synthesizers made out of 555s because of course to get sound out of a speaker, you just need a oscillating electrical signal. That oscillating electrical signal gets turned into an oscillating wave of pressure in the air by the speaker, which is what we detect as sound. And so you can make a square wave with the 555 and send that into a little speaker and have that tone coming out. And then if you have a potentiometer hooked up like we just showed, you could change that tone with the potentiometer. Lots of cool things you could do with that. You could make a little synthesizer keyboard out of just a bunch of 555s hooked up to buttons and just getting the exact right resistance in here to make each specific tone. So there's a neat idea. But what else can you do with ICs? So I've included in your kits a handful of other ICs, and I've given you a brief description of what they do here. They are the 4017, the 4019, and the 4511. I'll go through them briefly here with a few caveats, but I'll also leave it to you to just kind of go on the internet, Google around. You can look up IC projects, you can look up 4017 projects, you can look up 555 projects, and you'll find infinite ideas out there. Let's do a quick search, 555 projects. Look at this, a whole post full of 555 IC projects. If we even just go to images, we see a whole bunch of different ideas here. Oh, there's that toy organ. So there's that little synthesizer I was just talking about, an amplifier, all sorts of stuff. But what else did I include in your kits? Let's talk about each of these. The 4017 is another very common one to find. It's what's called a decade counter. Basically what it does, it's got 10 output pins and 1 input pin, and only one of those output pins is ever on. So we've got 9 output pins off, 1 that's on, and when the input pin receives a pulse, up and then down, that tells the chip to turn off whatever pin is currently on and turn on the next pin. And then it receives another pulse and it turns off that pin and turns on the next pin, and so on and so forth. So you could hook up that input pin, it's called the clock pin. You could hook that up to a little push button and have it cycle through a bunch of LEDs every time you push the button. But of course, things get more interesting when we combine ICs in interesting ways. What if you connected the clock pin of the 4017 to the output of a 555 oscillator, and now you've got the LEDs cycling through on their own automatically? This is what's called the Knight Rider circuit. If any of you are familiar with the old TV show Knight Rider, which had a car, and the kind of way that it showed the car was talking was this bar of LEDs that kind of flashed back and forth. So you can look up 4017 project and a lot comes up. We even see here, there, LED chaser circuits, there's the Knight Rider, and we can even see here there's a 555 and a couple 4017s. You can do it with just one 4017 as well. So lots of cool stuff out there. And of course, I have included the 4017 data sheet. Don't get too lost in the weeds with this. Just take a look at the pinout. This data sheet is for 2 different ICs. So whenever you're looking at a diagram here, just make sure you're looking at the 4017 diagram, not the 4022. So this is a functional diagram, gives you a bit of that visual view of what's going on. We've got a clock in and some reset stuff and some other stuff. And then we've got all of our output pins. They're in a kind of jumbled order physically on the IC. You can see their actual pin numbers here, and these are their numbers in terms of what order they get turned on or off in. And if we scroll down here, this is the actual physical terminal diagram with our VCC. Actually here it's called VDD, but basically the same thing. Hook that up to power, VSS here on pin 8, hook that up to ground. All of these numbered ones are the outputs. So there's output 0 and 1 and 2 and 3 is here and 4 is over here. So they're kind of jumbled. And then here's that clock pin. I wouldn't bother looking any closer on this diagram. Best bet is to just find circuit diagrams on the internet. And for the most part, when you find these, they will have the pin numbers on them. So you probably don't even need to look up that pin out, right? Look at this one, it's got all of the pin numbers here. And even for the 555, it's got both the pin labels like we saw in that other schematic, and it's also got them numbered. So you don't even need to refer back to the pin out. Another one that I've included is the 4019. This is a 4-bit binary counter. We talked briefly about how binary numbers work. So what this IC can do is output a 4-bit binary number. Basically, it has 4 output pins, each one representing a different place value in that number. And it's got an up and a down input pin. And so if the up pin receives a pulse, the outputs will increment that count. So the output pins that are representing that 4-bit binary number will change to reflect whatever the new 4-bit binary number is. Now that's just a 4-bit binary number. You could represent that with 4 LEDs and start to just understand how how binary counting works. If you wanted to be visual with it, you might want to try hooking it up to a 7-segment display. Now, you've seen 7-segment displays all over the place. They're this kind of display. They've got 7 little LEDs behind these bars, and depending on what combination of them are illuminated, you get a different number. Now, in order to drive this, because this of course has 7 inputs, and we've got only 4 coming out of our 4-bit binary counter, you could construct a complex sequence of logic, like using logic gates, to turn that 4-bit binary number into the correct signals for each of these inputs. But the easier way to do that is just use an IC that's purpose-built for that. So I did include an IC for that. It's called the 4511. It is a BCD to 7-segment decoder. Okay, BCD is binary coded decimal, basically a number that is in binary. And it turns that binary number into the 7-segment inputs. So into the 7 inputs that would need to go into one of these 7-segment displays. So theoretically, you could hook up a 555 clock signal to the 4019 counter so that this counter is incrementing every clock pulse of the 555, and then have those 4 outputs of the 4019 go into this 4511, which would turn those into the 7 inputs for a 7-segment display. However, I managed to make one small to medium-sized error in which BCD to 7-segment decoder IC that I got. I'm going to explain the issue, and if you want to get creative and do a bunch of research on your own and try and make it work regardless, I'll leave that to you, but don't feel like this is anything that like you need to do. So the issue is 7-segment displays come in 2 kinds. One is called common cathode, one is called common anode. In a common cathode 7-segment display, basically we've got these 7 LEDs and all of their negative ends are connected together, and that would just go straight to ground. And so what you would need to provide to this as a signal is 7 different signals and then a current limiting resistor. And if any of those signals is on, that LED will turn on, and they all just connect together to ground. That is a common cathode 7-segment display, and that is what the 4511 that I've provided you is built for. So it will produce the 7 outputs that are off unless that LED needs to be on. However, in your kits from Freenove, you actually have common anode 7-segment displays, which are the opposite. So in a common anode device, the positives of all of these LEDs are connected together, and you would connect that just directly to 5 volts. And it's from the negatives of these LEDs that you would connect a current limiting resistor to some signal. And if that signal is off, so connecting to ground, that actually turns on the LED, because then current can flow from the 5 volts that is shared between them all through that particular LED through its current limiting resistor, and then sunk through that IC to ground. So it needs the opposite kind of behavior, all of those signals on, unless that specific LED is supposed to be on, in which case that signal has to go off to turn the LED on. Confusing, backwards, is what it is, okay? It's just 2 flavors that these 7 segments come in. I didn't do my due diligence and check what came in your kits from Freenove, so that is my bad. So if you try to hook up a 555 into a 4019 BCD counter and take that BCD counter into this 4511 BCD to 7-segment decoder, and then those 7 outputs from the 4511 into the 7 inputs on your 7-segment display, which by the way has this pin out. So the middle pins here both go up to positive, and then all these other pins are the ones that are going to connect up to that 4511, but first through a current limiting resistor. You will get some symbols on your 7-segment display, but it's going to be the inverse of the actual symbols that you're wanting. So if it's supposed to draw a 0, you'll instead just get the dashed line in the middle and not the lights for the 0. So you can figure out a way to invert that signal and make the lows highs and the highs lows. You can use the NAND gate to do that. You would need a separate NAND gate for each of these, and you only have 4, so good luck. But the other thing you could do is basically make your own 7-segment display. Just take 7 LEDs, arrange them on the breadboard in this kind of a pattern, and kind of pretend. So you could do that as a little side project if you want. But basically, just find something interesting to do with these ICs, okay? Look up projects on the internet, noodle around on your own, and just kind of come up with some interesting things to do. And when you make something, just post it into the D2L discussions with me. That's the easiest way. A lot of people have already been doing that to show me their progress through this. And that really helps me in figuring out who's doing these modules so that I know who to register for the modules, first of all, and whether or not they're doing the work. So if you have any questions about that, just email me, hop in the Google Meets office hours. If you get stuck on any of these things, email me, Google Meets office hours or private discussions on D2L. The office hours is probably the best way because a lot of this is me having to kind of ask you some very specific questions about what's plugged into where. And if we're just kind of bouncing back and forth with emails or private discussions, that can take a while. But if you just hop in that Google Meet, we can get on a video call. You could point your webcam at your circuit or just kind of try to explain it to me. And we'll probably troubleshoot it that way. So that's all for the Net 1010 module, okay? We covered truth tables, we covered logic gates, we covered making some circuits using logic gates, and now using some other interesting ICs to make some different exciting things happen. And this kind of fundamental knowledge goes a long way in your understanding of electronics as we move on, knowing how to look at a pinout diagram and hook something up quickly on the breadboard, having a basic kind of understanding of what's going on with electrical signals. For the most part, we've just been visualizing them with LEDs, but in the long run, those signals serve purposes and maybe go into Arduinos to be sensed or measured, or go into other devices like we're seeing a little bit here of chaining together ICs, and everything just kind of builds from there. I hope you found this interesting. This is my favorite part of the course, is just tinkering around with ICs, building things on the breadboard and troubleshooting and seeing what's going wrong. I find it really exciting, and I hope you did too. Remember that there's a lot more in your kits than what we covered in this class. Some of it we touch on next year. Some of it we don't even touch on in the course, but you can find lots of information about how to use that stuff on the internet. We live in a wondrous age of unlimited access to resource and knowledge, and do make use of that, or get in touch with me and I can help you kind of muddle your way through any kind of bonus content that you're after. I hope I see some of you next year in Robotics 20. We do a lot of interesting things, a little bit more of this kind of electronics fundamentals, but we also look at actually building some robots to compete in a few different competitions. So have a great rest of your semester, enjoy your summer, and we'll see you next time. Bye.